Hello friends, today we are going to see the crystal field theory for octahedral complex. Now remember that when we consider any octahedral complex, when we consider any octahedral complex, let's take example that is Ml6 plus or minus N. Now this is the metal and this is what the ligand. Now here the ligand C is 6. Ligand C means what? The number of ligands that has been directly attached with the metal is what? It is the 6. That means, or we can call it as what? Coordination number. We can call it as what? Coordination number. So number is what? It is a 6. Now if you consider the diagram of this complex is like this one. This is at the center metal, this is ligand 2, 3, 4, 5, 6. Now this metal is what? It is specially the D block element. D block element. D block element. And when we think about the metal in the coordination number, we have to think about the d orbital. We have to think about the d orbital. Okay. Now here in CFT, we have to see the splitting of d orbital. The splitting of d orbital. Okay. Now the first thing is what? We have to consider the two cases. So case number one. Now case number one is when metal is alone. When metal is alone means if I consider any d block element, suppose if I consider Fe. Now when Fe, if I consider in alone, in absence of, what we can say that in absence of any ligand, what exactly happen? The electrons which is present in the d orbitals. Okay, the electrons which is present in the d orbitals. So at that moment, when I consider Fe alone state, this d orbital means the orbitals, the d orbitals, that is what? Dxy, dxz, dyz, dx square minus y square and dz square, they are having the same energy level. They are having the same energy level. So here the very first thing that I have to note that when the metal in absence of any ligand, the orbital which is present in the d orbital, they are having the same energy level. Okay, so these are called as what? Degenerate. These are called as what? Degenerate orbital. These are called as what? Degenerate orbital. Okay, so this the first idea that I am getting in absence of ligand. The second case that I am going to consider, that is very important and that has been considered in the CFT. So this is what my case number 2. Case number 2. When metal is with any ligand. When the metal is with any ligand. Now again I am going to take the example that is Fe H2O 6 plus 2. So if I have to draw the diagram, so I'll draw in this way. This is OH2, 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 OH2 and OH2. Now here we should have to note that when any ligand that is approaching towards the d block center element, what exactly happen? The electrons which is present in the d orbital and the electrons which is present in the which is present with the ligand, the force of repulsive that has been taking place between the metal and the ligand. So as a result of that, what exactly happened in the previous case? the orbitals of the d which has the same energy level, we can call it as what, degenerate orbitals, that degeneracy that has been lost when the ligand is approaching towards the metal. Okay, so that means degeneracy that has been lost. Okay, so what exactly happened, the d orbital that will get splits into two orbital, into two sets. That is what the first set is, what the first set is what, here I'm going to write the set number 1, dx square minus y square and dz square. This is what my set number 1. And the second set, that is called as what, dxy, dxz and dyz. Now out of these two set, this is having the highest energy. This is having the highest energy, and these are what, the lower energy. These are occupy the lower energy. Now the reason is what, why this is happening, so that is very important thing, why this is happening. So now if I consider this ligand, now this is what my, if I consider this is what my z axis, this is what my z axis, right? This is what my x axis, and this is what my y-axis. Now if you see the d orbital, if you see the d orbital, what exactly happened, this dx square minus y square and dz square, they lies along the axis, they lies along the axis. That means, suppose this is what my diagram. Okay, suppose if I have to show dx square minus y square, how I'm going to show it, this is what my x and this is what my y. So I'll show it like this one. Okay, I'll show like this one. Okay, that means my lobes, they are directed along the axis. If I have to show the diagram of dz square, how I'm going to show it, this is what my x and this is what my z axis. So I'll show like this one. Okay, so this is what my dz square, this is what my dx square minus y square. Now what exactly happened, if I consider the octahedral complex, the ligands are approaching, see, all the ligands, they are approaching along the axis, they are approaching along the axis. So what exactly happened, if the ligands are approaching along the axis, the orbitals that are directed along the axis, they will get what we can say, that there is a maximum force of repulsion between the lobes, between the orbitals that has been directed along the axis, and as a result of that, these orbitals that occupies the higher energy level, right? So as a result of that, dx square minus y square and dz square, they occupy the highest energy level, whereas the orbitals, that is dxy, dxz and dyz, they are directed in between the axis. So if we have to show the diagram of dx square minus dxy orbitals, that is what dxy orbital. So how I'm going to show the diagram like this one. So this is what my diagram of, this is x-axis, this is y-axis. So angle is what, it is 45 degree. This is what my dxy. Now here if you see, the orbitals, they are not along the axis, they are in between the axis, making an angle of 45 degree, making an angle of 45 degree. If the second orbital, that is what dxz, I'm going to show it like this one. So this is what my dxz, this is what my x-axis, this is what my z-axis. The angle is what, it is 45. The next one is what, dyz. So this is y and this is what my z. This is what, this is yz. So angle is again the 45 degree. That means The that means the orbitals, they are not along the axis. So definitely what exactly happened, there is a less repulsive forces in between in between d orbitals of dxy, dxz and dyz with that of ligand, and hence they occupy they occupy lower energy. That means dxz, dyz and dz, they are having lower energy. Now let's see how these things can be diagrammatically that we are going to show. This is what my d orbital, this is 1 2 3 4 5. So this is what my d orbital, okay, in absence of ligand, in absence of ligand, okay. Now once the ligand that has been approached, the energy that will get rise up, 1 2 3 4 5. This is what my d orbital in presence of ligand. But what exactly happened, the ligands, but what exactly happened, the orbitals that has been directed along the axis, they have been repelled to a greater extent, and that's why their energy is what it is little bit higher. So this is what my dx square minus y square, this is dz square, whereas this is dxy, dxz and dyz. Now see, in order to stabilize this field, the extra amount of energy that has been required, and that is called as what, CFSE. CFSE means what? Crystal field stabilization, crystal field stabilization energy, crystal field stabilization energy. So what exactly happened, if I consider this is what my average energy level, this is what my average energy level, which is called as what, barycenter, which is called as barycenter. Now, so barycenter means what, average energy is what, it is always zero, it is always zero. So above this barycenter, this is what the energy, that is we are going to call it as what, 3 by 5 delta 0. Delta 0 is what, it is the crystal field splitting. Delta 0 is what, here I'm going to write it here, delta 0 is what, crystal field crystal field splitting in octahedral octahedral geometry octahedral geometry. So this is what my 3 by 5, okay. And below the barycenter, it is 2 by 5 delta 0. If I consider it, so this comes out to be 0.6 plus 0.6 delta 0, and this comes out to be minus, this is minus 0.4 delta 0, 0.4 delta 0, okay. So if we have to find out the crystal field stabilization energy of any complex, we can find it out by using the formula CFSE, that is equal to minus 0.4 into n T2G delta 0 plus 0.6 into n EG delta 0 plus P. Now here P is called as what? Pairing energy. P is called as what? Pairing energy. Now remember that here delta 0 is what? Delta 0 means what? This is what my splitting. This hole is called as what? The delta 0. This is what my splitting in octahedral complex. Now this splitting will depends on, it totally depends on the charge on the metal, and it depends on the nature of ligand. Now remember that if the ligand is strong, if the ligand is what? It is a strong ligand, and charge on metal is high, then delta 0 is greater than pairing energy. Delta 0 is greater than pairing energy. And the second thing is what? If ligand is weak and charge on metal is low, so in that case my delta 0 is what? It is less. Okay, so we'll take one example here so we can easily understand the thing. Suppose here I'm going to consider one complex, that is CONH3 6 plus 2, and here I'm going to consider the another complex, that is CONH3 6 plus 3. Now both are octahedral complex. Here the coordination number is what? It is 6. Here the coordination number is what? It is 6. Now here NH3 is what? It is the neutral ligand. It is neutral ligand, so definitely the charge which is present on ammonia is what? It is 0. So therefore oxidation state of cobalt is what? It is plus 2. Here the oxidation state of cobalt is what? It is plus 3. Now if we consider in both the cases, the cobalt is present in what? It is high oxidation state. So definitely what we are going to observe, that whenever the metal is present in the high oxidation state, even if the metal is with the weak ligand field, that ligand will act as a strong ligand field. That means what exactly happened, which case that has been here obeyed. So here delta 0, here the splitting is what? It is the more. So delta 0 is greater than the pairing energy. So how this will take place, that we are going to see. So CO2 plus CO, that is what? 27. So outermost electron configuration 4s2 3d7. So CO plus 2, that comes out to be CO plus 3, sorry, CO plus 3 is 4s0 and 3d6. So d6 system 1 2 3, this is 1 2, this is my EG, that is called as what? doubly degenerate. This is doubly degenerate, and this is what? My T2J, that is what? Triply degenerate. So we have to fill the 6 electrons. So 1 2 3. Now the fourth electron does not goes into the EG orbital. Why? Because the delta 0 is very large. So instead of going into the higher energy level, it will get occupy the lower energy orbital. That is what? Fourth, 5 and 6. So here if you can observe the number of unpaired electron, n is what? It is the number of unpaired electron, and that is equal to what? 0. Okay, so the hybridization here, the hybridization in this case, we are getting it as what? D2sp3. Now this is what? My inner orbital complex. This is called as what? My inner orbital complex. Now let's see the another case, that is what? CO2 plus. Now here the electron configuration that becomes 4s0 3d7. Now how the splitting that will take place? Let's see, 1 2 3, that is T2J, and this is what? My EG. Now we have to fill the 7 electrons. Now this D7 system is what? It is the weak field. So this is what? My high spin complex. The weak field that always behaves as a high spin complex. We have to fill how many electrons? 7 electrons. So my delta 0 here in this case is what it is. Delta 0 is small. So what will happen? Electrons once fill in T2G orbital, the fourth electron will goes into the higher energy orbital. So 1, 2, 3, 4, 5, 6, 7. So here what exactly happened? The 7 electrons will occupies in the T2G orbital. Okay. Why? Because delta 0 is what? It is what? It is very small. So here in this case, this complex shows the hybridization of sp3d2, that is outer orbital complex. It occupies the outer orbital complex because of the less charge which is present on the plus 2. Now it has the unpaired electrons, so definitely it behaves as a paramagnetic. It behaves as a paramagnetic. Okay, thank you.